This is a recording to go over, the basics of improper integrals. So might as well get started. Let's define what I even mean by that. So assuming I have some function, let's just say, here's my function, and it looks like this, and it basically has the x-axis as an asymptote. If I start, if that's A, and I want to compute the area underneath the curve from here to any point, that's easy. I just go to, I might do the integral. If I wanted to stop at, say, B, well, then I would calculate, if this is F, I would calculate the integral from A to B of f of x dx. And then I'd be happy with that. Now, if I didn't want to stop at B, if I wanted to keep going out to infinity, I wanted to calculate the area from A, and I never wanted to stop. I wanted to see what the successive areas tended toward, if they ended up going toward a number or if it just started getting bigger and bigger. Then this integral would be, I guess, sort of defined this way: the integral from A out to infinity of f of x dx. Now, a little bit of a problem with that is infinity is a difficult, not really a number, it's harder to deal with, so we have to handle that in a slightly different way, and I'll show you that in a minute. The other type of improper integral that we could have would be where, if I have a function f and there is some sort of vertical asymptote, and I graph the function and it shoots up, and from here, if this is A and the asymptote occurs at B, I want to see if from A, if I find that area there, is it a finite amount, or as I get closer and closer to B, does the area just get infinitely larger? Does it keep on growing, or does it ever stop? So in this case, my integral is easy enough to write down. It's the integral from A to B of the function f of x. But the problem that I'm having is, as I approach B, I have an asymptote there, so I have to handle that in a slightly different way. And that's one of the things that we're going to address right now. So, might as well get to it with an example. One more thing before I actually do. If in either case, if this area actually approaches a number, in other words, there's an answer for it, we say that the integral, this term is going to come up, converges. My pen's acting a little funny. The area converges. If not, we say the integral diverges. Okay, so when we refer, now those terms are going to come up again later on. We do sequences and series, but for now we're going to use that. Basically what it means is, if the integral approaches a number, if that infinite area actually isn't infinite, if it approaches a number, we're going to say it converges. Otherwise it diverges. So let's actually start up with an example. Let's do this. Over here on the right, on the left rather, what I have is I have a picture of the function 1 over x to the third. So it's 1 over x to the third power. And just so you can see it, if I move this slider here, if I actually take this and just move it, you can see as it moves to the right, we collect area, more and more area collects. But as we move to the right, the function drops fairly fast, and the amount of area that's accumulated each time is very, very, very small. So then the question is, does that area, like the one I always like to refer to is something like this. If I have, like consider the number which you've all considered before, 0.11111 repeating, never stops. Well, you can look at this as an infinite sum. This could be considered 0.1 plus 0.01 plus 0.001 plus 0.0001, etc. And it's never going to stop. And what that means is, even though there are infinitely many of these terms, it's never going to exceed a certain value. And the question now becomes is, does my integral act that way? So let me give a crack at having you show how this goes. So what we're going to look at right now is this. The integral from 1, we're starting it at 1, to infinity of the function 1 over x to the third dx. Now, like I said before, I don't really like that top bound being infinity, so the way we handle that, since this is a definite integral, we do it this way. We say the limit pen is acting funny, as k goes to infinity. You could choose any letter that you want, it doesn't have to be k, of the integral from 1 to k of 1 over x to the third dx. So now what we've done is we replace the infinity with a definite number, so we're going to be able to take the antiderivative, evaluate it at the two bounds, and then take the limit of that. And that's how we get around the infinity problem. So the way I would handle this is I would say this is equal to limit as k goes to infinity of the integral 1 to k of x to the negative 3 dx. So the rule, which is pretty easy, limit as k goes to infinity of, now the antiderivative of this, we add 1 to the exponent and we divide by the new exponent. So that's going to be negative 1/2 times x to the negative 2, or just over x squared on the bottom. And we're going to evaluate that from 1 to k. So this becomes the limit as k goes to infinity of negative 1 over 2k squared minus negative 1 over 2 times 1 squared. And obviously this becomes a plus, and I think it doesn't require too much of an argument to say that this is going to 0 as k goes to infinity, so that's out, that goes to 0. And what I'm left with is just 1 over 2. So what this tells me is this integral that I've just tried to evaluate does indeed converge. In fact, we found out that it converges to 1/2. So if I were able to sum up the area forever, it would go to 1/2. Now obviously I can't do that, but that's the upper bound. Now, if we take this, let me just scroll this off. Let's look at another function. Let me turn that one off and turn on that function. Let me just back this away. Okay, now what we're looking at is 1 over x. All right, and as I do this, you can see, look at the area accumulate. It does the same thing. It accumulates more and more area every time we move over as we extend our bound out. All right, the area doesn't, but it keeps getting smaller, but it's not nearly as small as the other one was. Take a look at the other function. See how it compares? Drops a lot faster. So that was 1 over x to the third, and the blue one is 1 over x. So let's see what happens when we attack this one. Okay, here we go. So we're now going to look at the integral from 1 to infinity of 1 over x dx. This is going to become the limit as k goes to infinity, integral 1 to k of 1 over x dx. Now, the difference here is I can't do the reverse power rule with this integral. You have to know that the antiderivative of 1 over x is the natural log of x. Now, since we're already greater than 0, we don't have to worry about absolute values or anything like that, but there'll be more on that talk when we get to differential equations. So right now what I have is this. When I evaluate the integral, I have the limit as k goes to infinity of the natural log of x evaluated from 1 to k. Now you should start to see the problem with this already. This becomes the limit as k goes to infinity of the natural log of k minus the natural log of 1. And what ends up happening here is, if we know anything at all about the natural log, is we know that this function increases without bounds. So this limit is infinity, which in this natural log of 1 is 0. So basically what this is telling me is this integral diverges. There is no limit on top of the area that we're looking at. Okay? So that's what we have there. Now what I wanted to do is I wanted to consider an integral of another type, an integral of one that has an asymptote. So if I were to look at the function, let's look at this function. F of x equals 1 over the square root of 1 minus x squared dx. Now, consider a question, if you would, for a minute. Why did I pick this function? Number one, I can integrate it, and while I do the problem, while I'm setting everything up, you should be thinking to yourself, what was the antiderivative of that function? So, ready? Let's take a look at it. This function is an improper integral of the other type, and it looks like, if I were to graph it, I'm only going to graph it greater than 0, so it goes over on both sides. But essentially, it comes down, comes here, and then it shoots back up as we approach 1. So 1 is an asymptote. So my question is going to be this. Is this area between 0 and 1 of this function, is the integral going to be convergent or divergent? So here we go. We set it up this way. The antiderivative from 0 to 1 of the function 1 over the square root of 1 minus x squared dx. Now we know that we have a problem at 1, so I'm going to change this to the limit as k approaches 1, integral 0 to k of 1 over square root 1 minus x squared dx. Alright, so I'm hoping you remembered what the antiderivative of this was. The antiderivative of that becomes limit as k approaches 1 of, did you figure it out? Arc sine, pen's messing up again, arc sine of x evaluated from 0 to k. So this becomes limit as k goes to 1 of arc sine k minus arc sine 0. So, as k goes to 1, there's no problem with any of these limits, so they're basically easy to take by substitution. As k goes to 1, the arc sine of k, another way to ask yourself the question if you've forgotten is you could say, you know, I can substitute 1 in here since there is no issue, but the sine of what gives me 1? And I hope you remember that the answer is going to be pi over 2 to that question, pi over 2. Minus, and the arc sine of 0 is 0, so there it is. So this integral is going to converge upon the number pi over 2. Okay? So what I've given you in this video, I'm going to put more videos up of this, but what I've shown you is what the basics of an improper integral is, how they work, the two different types, and how you adjust the fact of dealing with infinity. Alright, so I hope this helps, and look forward to the next one.